Next, yes, next is surface tension. One of the most beautiful property of our total fluids among with all properties. Have you ever seen one ant dead at one surface of water into your bowl? Have you ever seen ever? So there is just surrounded to ant's body. There is one suppression parts of surface or of that particular liquid which is there. So that suppressing part is nothing but surface tension. So tension means if you can notice this figure, so if I take this part or these molecules, okay, so here all pressure comes in from all directions are from same liquid, okay, same liquid. So obviously here cohesion in dominance, but take if I take one molecule which is situated on surface only. So then here are these are all water molecules, but above surface all are air molecules. So due to this, here will be from cohesion to adhesion will be dominated, and that's why all molecules on the surface they all got under stretching, and that's why you can see some depressed part surrounded by uh, that floating ant. So here are three examples of surface tension. First one is droplet, second one is bubble, and third one is water jet. If I could have to clear, or if I could teach you in better way, then it would be more happy to me or more joyous to me. But right now, if I'm focusing your exams, then I have uh, to be prepared you all in a very concise manner. So that's why I'm not here explaining you how this formula we have derived. But yes, for sure, I will be teaching in that manner too. So right now, droplet. So you have to just remember these three formulas, okay, and concept of surface tension. What is surface tension and how it generates, why it generates, okay. So a droplet has change in pressure is equal to 4 sigma by d. Bubble has change in pressure is equal to 8 sigma by d. Why it is 8 sigma and here it is 4 sigma? Because if you see very clearly and cleverly, then you will get some rainbow colors here and here also. So why these rainbow colors you are appearing? Because here in bubble there is two films formed, okay, there is two films are formed, so due to which here you can see some spreaded colors to your eyes. So that's why here in formula we came as from 4 sigma to 8 sigma by d, and in water jet the change in pressure is equal to 2 sigma by d. Now just focus on to capillary or capillarity. Here you can see clearly there is one liquid which is water and there is another liquid which is mercury. If you put which is capillary tube which is having like about 4 to 6 mm in size, if you keep it into one water jar, then some water will get rise and form this curved shape or convex shape, which you call it as this shape is called it in capillary, you call it as meniscus, right? And mercury gets fall down when it you insert capillary tube into mercury solutions, right? So if I draw this meniscus, so here is one stress, and if I resolve it into two components, then straightly I will write sigma cos theta. So simply to remember this formula, you have to just remember H is equal to plus or minus. Why plus or minus? Because water is rising and mercury going to falling. So that's why positive and negative, positive or negative 4 into this one vertical component, which is sigma cos theta divided by gamma d, or you can write rho g also, which is rho gd. Again, I'm repeating, h is equal to plus or minus 4 into sigma cos theta divided by gamma d or rho gd. I'm just wrote here already we studied points just to recall you in a quick succession. So first one we studied today, fluid continuum, Euler's, which is fluid continuum, which is given by Euler's, and control volume approach. Obviously, there is two approaches. Which one? Those first one is Lagrangian approach, and second one is Eulerian approach. Then fluid properties, obviously, first one is mass density, then wet density. Okay, then we saw this beautiful relationship: wet density is equal to mass density into g. Okay, so we studied all their standard values and their units. So these all points you have to remember. Okay, make sure of it. So then specific gravity we studied. So what is specific gravity? Nothing but density of given liquid. Okay, divided by in denominator density of standard liquid. So after specific gravity, we went to the viscosity. Before jump into viscosity, we just briefly studied friction, which are those two types of friction, which is dry friction and wet friction. And we studied here, or we started to study for fluid mechanics, which is wet friction or viscous. So here Newton gave us one relationship: shear stress is directly proportional to du by dy, right? And apart from dynamic viscosity, there is also one viscosity which is kinematic viscosity, and there is the she got a very simple formula which is dynamic viscosity by mass density. Then we studied effect of temperature on dynamic viscosity and kinematic viscosity respectively. Then we come to new compressibility and relationship between bulk modulus, which is inversely proportional to each other. Then we discuss types of fluids. Okay, I already had practice, or I already had very much elaborate how to recall all fluids, which is Newtonian and non-Newtonian, stress dependent or time dependent. So then we came to know about surface tension. Uh, three application of by nature given us. First one is droplet, then bubble, and third water jet. Then capillarity, and last one is, I think we have not discussed yet, but right now we are discussing. So here is one glass surface here. Okay, so on a glass surface, here is one drop of mercury, and here is one little amount of split water. Okay, so what you observed first, this droplet of mercury form a obtuse angle from obtuse angle to the glass surface, and this splash water form an acute angle to the glass surface. Why this form obtuse angle? Because here, due to very much cohesion is in dominating position in mercury molecules. Okay, so there is very less contacted area with glass surface. Okay, so that's why here they form obtuse angle to the glass surface, and but not same in the case of water molecules. Here they form an acute angle. Why? Because all water molecules are already attracted towards the molecules of glass surface. So what attractive force here is dominated, which is adhesion is most strong and most dominated here. So that's why the water get forms acute angle to the glass surface. So after studied all properties of fluid, so we are now going to start. First is types of pressure. If you can able to remember this carefully, this diagram or this page, so get actual you will get actual result, or you will get all corrected your answers regarding pressure. So what I drawn here. So at horizontal, I put here P atmosphere, and at some angle, I put P absolute, and between them, there is one pressure gauge or pressure vacuum. So you have to be just imagine these three lines only. Okay, make sure with yourself you are well listening to me. If you just remember these three lines, so what you are observing right now. So in middle, what I written here, P atmosphere, if zero. So on this line, atmospheric pressure is already zero. So if you go further ahead, or if you go further above, then then you get some pressure. So that pressure, which is known as absolute pressure. Here you get absolute pressure, P absolute, and here also you get absolute pressure. Okay, but if you consider P atmosphere is equal to zero, which is on our middle line, then here you have to, if you are going above, then obviously here is a positive, and if you are going downward, then obviously you are using negative. So in formula, it should be reflecting like this: P absolute is equal to P atmosphere plus P gauge. Okay, on this line, at every point, you will get this amount of pressure. How much it is, which is P atmospheric, plus how you goes to above from atmospheric pressure is zero. Okay, so P atmospheric plus P gauge. And if you willing to go downward, then you will get P absolute 2, but you have to use this formula. P absolute is equal to P atmosphere, okay, P atmosphere minus P vacuum. This is also P gauge pressure, but we call it as vacuum pressure. Okay. Gauge pressure is nothing but a pressure we measure from gauges. So after remembering these three lines, so instead of remembering these three formulas, I think I am giving you pretty much clarity. So now we have to study pressure measurement. Okay. Before heading towards pressure measurement, let me tell you all, pressure measurement is one of the most easiest. Okay. So I have divided further it into two parts. First one is A, units, and second one is devices, obviously. So units, what are the units regarding pressure? Obviously, one is P atmosphere or atmospheric pressure, then Pascal or Newton per meter square, then torr and bar. So here I wrote already, one atmosphere is equal to 101,325 Pascal or Newton per meter square. Then one atmosphere is equal to 1.01325 bar. Third is one atmosphere is equal to 760 torr. And fourth one is pressure head. They ask in form of pressure head, or they just ask in form of how much H, okay, in terms of of liquid. So you can call it as liquid column height. So here I put some very little derivation. If this is one tube, okay, so at surface area, we assume, or we take here one energy present, which is potential energy, is equal to mgh. Okay, we know already density. Okay, density is equal to nothing but mass per unit volume. Okay, so after taking volume as 1 meter cube, so we will get density is equal to, or density is nothing but mass. So already we used one potential energy, which is mgh. When it you take density is equal to mass. So you write it as P is equal to, instead of mgh, you can write it as rho gh. So if I rearrange them, uh, it comes as h is equal to P by rho g. It means nothing but this much height. Okay, this much height is going to be rise when P is applied on a liquid having density. So if I further calculate for mercury, if I consider, or if I assume mercury having volume of 1 cubic meter, so already we know 1 atmosphere, or at 1 atmospheric pressure, how much Pascal it is? 101,325 Pascal. And mass density of mercury is 13,600 kg per meter cube. These two things already we know. So, and we just derived one formula, which is pressure is equal to rho gh. So if I put all values, and if we get h is equal to 760 mm, so how you can read it? H is equal to 760 mm. H is equal to 760 mm of Hg, means 760 mm of mercury, for how many cubic meter? For 1 meter cube of volume. So it is nothing but 1 atmosphere is equal to 760 mm of Hg. And when it comes to water, uh, here only will change density of water, which is 1000 kg per meter cube. One atmospheric pressure remains same, which is 101,325 Pascal. Then here here we use for this formula only, P is equal to rho gh. If I put all values and compute H, so in case of water, H comes out to be 13.13, means 10.13 meter. And when it comes to mercury, you just calculated it, so it comes out to be 760 mm. Just see the difference between two of them. Okay, so what I'm trying to tell you, if I put 1 atmospheric pressure, okay, if I put 1 atmospheric pressure, then water will rise up to 10.13 meter heights, but mercury will rise only just 760 mm, which means आय जस्ट रोटेट इट ॲज इन मराठी. म्हणजेच 1 atmospheric प्रेशर लावल्यावर मला 10.13 मीटर उंचीपर्यंत पाणी वर घेता येईल, बरोबर, एका ॲटमॉस्फेरिक प्रेशरवर. आणि तेच जर मी 1 atmospheric प्रेशर लावल्यावर मर्क्युरीला, जर मी 1 atmospheric प्रेशर लावतो, तर मर्क्युरी फक्त माझी 760 mm हाईटवर पोहोचू शकेल. ओके, एक जस्ट एक्झाम्पल मी घेतलेलं आहे. ह्याच काइंड ऑफ तुम्हाला एकतर जास्त न्यूमरिकल्स येणार नाहीये, हे तुम्हाला सुद्धा माहिती असेल. डिरेक्ट रिक्रुटमेंट एक्झाम्स आहेत, जेई लेवलची एक्झाम आहे. सो जास्त ऍप्लिकेशन बेस्ड ते न्यूमरिकल्स थ्रू नाही विचारणार तुम्हाला, पण तुम्हाला हे माहितीच पाहिजे नक्की कशाचं काय रिलेशन असतं. त्यासाठी मी हे घेतलेलं आहे एक एक्झाम्पल. ओके, if if P gauge 7250 Pascal and density of oil 900 kg per meter cube, these two values are given, then they ask to us what is absolute pressure head for oil. So you have to be well aware about, if you have to require, or if they ask about absolute pressure, so you have to first get know absolute pressure to convert it into height, because they ask not just absolute pressure, they ask you about absolute pressure head. Okay, so to get absolute pressure head, you have to know one pressure, which is absolute pressure. So 1 atmosphere, you already know 101,325 Pascal. And if I put your formula, which is P absolute equal to P atmosphere plus P gauge, which is already I mentioned it into those three lines. Just recall it, or just go back and then come here again. Then already I put all values, and then I get absolute pressure, which is 108,575 Pascal. Then if I use this formula, P is equal to rho gh, and if I reshuffle it, then I get height. After using pressure, it has absolute pressure. So I get, after using absolute pressure, I get absolute pressure head, which is comes out to be 12.30 meter of oil, right? So by all this, after studying, you will get to know very clear when it comes to pressure measurement. And just last topic is remain, which is to measure pressure, which devices we use. Okay, so first one is barometer. So we use barometer as to measure atmospheric pressure only. Remember this. Barometer we use to measure pressure only atmospheric pressure. And barometer obviously it gives approximate value, not as much corrected value like manometer or piezometer does. And piezometer we use to measure moderate gauge pressure, and manometer we use to measure moderate and high pressure. So manometer we already using in our lab of fluid mechanics, which is a single U-tube manometer and differential U-tube manometer. Before analyzing or observing this manometer, just remember one principle, one absolute principle here is what I'm going to tell you. Pressure at same level, okay? Pressure at same level in same liquid is always same. Just look at here. When I denoted A, okay? Okay, where I dotted A, okay? Or and what I'm saying, pressure at same level in same liquid is always same. This whole principle we are about to, or we are going to use while forming one equation to get resolve manometer, to get our to get pressure, various pressure. So single U-tube manometer we use on principle, or single U-tube manometer we are using for to get point pressure, and differential U-tube manometer we are using to get pressure difference between 2 points. Okay, so just remember, if we are going downwards, then pressure we consider it as just use it as positive sign, and if you are going upwards, then consider it as negative sign. So right from here, point A, so here is pressure A at point A, then we have to come at this manometric liquid upper surface. So above that, here there is a height, okay, which is y, okay, height which is y. And what is our formula? P is equal to rho g h. So what is here? H is y, and rho is obviously density of water, so rho w into g into y. then then we we reach at this point till now. Okay, so we have to reach above, or we have to reach up to this point right now. So that's why I'm going from downwards to upwards. So I'm using here negative sign. Then this is manometric liquid. So rho m into g into manometric liquid's height, which I already denoted it as x. So is equal to 0. So in this way you can form, just clear your basics, so it will be more beneficial and you will get more clarity while solving. And if I'm going to discuss about differential U-tube manometer, just same principle you have to apply here only. Just remember, here we get, or we observed, there is like it can be two or three liquids. If we are going to measure pressure difference between two same liquids, then you are going to observe two liquids only, which is first one is manometric liquid, and then second one is you are going to measure that particular liquid. And if it is not in that case, so you will observe three liquid if you are going to measure the difference between two points or two liquids. So here one question get arise, if you are well concentrated throughout this my study hours. So why mercury used as barometric and manometric liquid, isn't it? Didn't you find any strange? why we use only mercury? So answer is, there is two constraint of mercury which having. First one is, mercury has very low vapor pressure. Okay, mercury has very low vapor pressure, and second one is, mercury having very high density, very high density. We already calculated above, right? When you applied one atmospheric pressure, water will arise in how much quantity? Water will arise at 10.13 meters, and mercury is just to move upwards in amount of just 760 mm. So why it is so? Due to this phenomena, mercury having very high density. And first one, what I told you, mercury having very low vapor pressure. So what is vapor pressure? What is vapor pressure? At one stage, okay, liquid molecules behaves as liquid, and gaseous molecules converts into liquid molecules under certain pressure. Okay, can I repeat? What is vapor pressure? At one certain stage, at one certain condition, liquid molecules behaves as liquid, okay, but for gas molecules, then trying to convert it into liquid molecules under certain pressure. That certain pressure we call it as vapor pressure. So just remember, to your better understanding. And I'm about to sign off our current first lesson of fluid mechanics, which we already started. I hope we will go like this way only, and I will get your feedback soon. So take care. Okay, Jai Hind.